Alrighty, welcome back to operating systems. So today, another fun short lecture. We like short lectures because it means we are almost done. So we have 2 more content lectures. Then I will chill out on you since your exam is the 7th. And we'll have 2 review lectures. So you can be well prepared for it. No excuses not to do well. So let's wrap up today fairly quickly, and then you should be working on lab 6, so that is done before the exam. So let's get into memory allocation, something that our operating system has to do that you might get into more details with in other courses. But we've already done this. Some of you have used this for the lab. So static allocation is the simplest strategy. So if I create a fixed size allocation in my program, if I just do like a global variable char buffer size 4096, the size of a page, well, this memory doesn't randomly appear for free. We probably can guess what actually happens now. So when your program loads, which is like that ELF file we explored right at the beginning, the kernel will go ahead, read that file, know what memory your compiler wanted, then loads. It'll set aside that memory for you, allocate pages before your program actually starts running. And then when your process starts running, that memory exists as long as your process exists. There's no need to free them. As soon as your process terminates, all that memory is freed by that kernel. So that is the simplest thing to do, but not the best thing to do in most cases. So you might only conditionally require some memory. So static allocations are sometimes wasteful because they exist for the entire lifetime of your program. So if you only need a gigabyte of memory for a few nanoseconds, well, if it's all statically allocated, you have to set aside a gig whenever your program loads, and it never gets freed again, even if you only use that for a little bit of time. You also might not be able to do any static initializations because you might not know the size of the allocation at compile time. You might only know it at runtime. So static allocations also need to account for the maximum size if it's something that can vary, which again will waste a lot of memory. So where do we typically allocate memory dynamically? Well, our 2 main choices are the stack and the heap, which we should both know about now, right? Everyone should have had lots of practice from 105. So let's make sure we know what we're doing. So stack allocation, there's other ways to think of it that maybe you haven't thought of before, so it's mostly done for you in C. So if you have a normal variable int x, well, you know that that lives somewhere in memory. It lives on the stack, and it is 4 bytes large. The reason people like using C as opposed to assembly is because C will go ahead and set aside that space for us on the stack. There's actually a function call we can make that can ask for memory from the stack. You just probably never made it before and probably don't know it exists. So has anyone ever used alloc-A? So that is asking for memory from the stack. So that will adjust the stack pointer for you and return an address to that base memory. So if you have int x in your program, the C compiler is actually going to insert a call to alloc-A, the size of whatever the data type is. In this case, it's an int, so it's 4 bytes. And then that's where it will live in memory. So the rule behind the alloc-A allocations is you don't have to free it. As soon as the function returns, goes out of scope, whatever you want to think of it, that memory is freed. And in this case, just restores the previous stack pointer, probably not going to overwrite any of the information or anything like that. Just reset the stack pointer, so it doesn't matter how many allocations you do, just resets the stack pointer, and it's all essentially freed for you magically. This doesn't work, though, if you try to use the memory after returning. So let's take a little review here. So here is a short, silly program I have written. It has a main function that calls foo, foo returns a pointer to an int. I capture it in a value called p. Then I print off whatever the address of that pointer is, right? Then I just return 0, so nothing should happen. In foo, I do int x, so x is on the stack, right? I see some head shaking. So x is on the stack, yes? And then here I print off the address of x. So it lives somewhere in memory. That should be an address on the stack. Then I return the address of x, which is just a pointer, right? So should this line and this line print the same value? Yes, right? So they should print the same value. I print address of x, then I return x. C is copy by value, so the caller gets a copy of that value. Shouldn't be any different, right? And then we write it to the variable p and just print off. So these two print statements should absolutely print the same address, right? Anyone disagree with it? So make sure everyone put their hands up. They agree. Same value, both print lines. All right. Everyone agrees. So let's run this. You're all wrong. Help. So, if we paid attention to our compiler, remember, so this address of x here, right, that is an address of my local on the stack. If I return from this function, x should only exist as long as foo exists. If I return from it, it shouldn't exist anymore, right? Well, technically, this is undefined behavior. So C can do whatever the hell it wants. So it just changes that value to a 0 so that you crash. So if I look at this too, it says, I actually got a compiler warning, which I ignored. It says address of stack memory associated with local variable x returned. I should not do that because it's technically undefined behavior. So it can do whatever it wants. So if I wanted to make sure these two lines printed, I worked with compilers, so this is really easy to actually fool the compiler to not do this weird thing where it just makes it equal to 0. So if I create a new variable called p in function foo, and then assign it the value of address of x, and then return p, I see that warning disappears. So I'm now not taking the address of a local anymore. According to the compiler, I'm just copying the value of a pointer called p, which is fine. So if I compile this again, I get no errors or no warnings, and then it actually prints the same memory address because I have now fooled it. And this is what you all raised your hand for. So this should be the more expected one. So I basically fooled the compiler. I was like, don't do that undefined behavior stuff because I won't take the address. I won't return the address of x directly. I'll do it a bit indirectly and fool you. All right. So the reason why the compiler is trying to do this, so let's say here, if I print, if I just print the value of x, okay, don't need to cast you. X should print what? X equals 1, right? Okay. What if here I just print, I dereference p and print whatever value that is? What's that going to print? So for this line, let's see. Hands up for garbage. Got a lot of garbagers. Okay. 0. 1. Got 1, 1. Garbage 1, 0. That's probably it. Let's try it. So compile it. Congratulations. Only one person got it right. Anyone guess why that is? Yeah.
You didn't do like a function called overwrite the value of it so that it's still in memory.
Yeah, well, I got lucky essentially. So, I use some variables on the stack. I call foo, more variables on the stack. X probably points somewhere to here. I return from foo, and I'm still pointing up there, but I just unwind my stack, go down to the next function. That value, I could overwrite the old values, but that is slow. Fastest thing to do is leave it alone. So I print, and then it just prints the old value. So if I change it to, I don't know, 42, it should also print 42, right? So prints 42 both times. Okay, cool. What about if I do that? So this should print 42, right? The first line. What does the second line print? $42. 1. 0. Garbage. -1. All right. Well, let's see. 0. Which is different than the last lecture. Essentially, it's garbage. So, why does that print something different? Well, it's pointing to somewhere on the stack. First time I called printf, it read the original value, but printf is going to use the stack, so it probably overwrote that value with something. Today, it seemed to be 0. So it just overwrote that with 0, and that's why I got 0. Last lecture, it was -1. Undefined behavior, I'm pointing to some invalid memory. So, moral of the story is, we shouldn't do that, right? Causes lots of fun problems. So do not point to something on the stack. We saw that a bit once we talked about threads and communicating between threads and all that stuff. But here is another reason not to do that, because this is very confusing, is it not? So I dare you to try and debug this. You probably can't. So anyways, that was the sidetrack. So most of the time, to avoid this, right, if we wanted that memory to live past the lifetime of foo, we have to use malloc and friends. So they're the most flexible way to use memory, but also the most difficult to get right, because we have to properly handle our memory lifetimes, which means you have to properly free it, and you have to properly free that memory exactly once. So, few ways to shoot yourself in the foot. If you don't free it as soon as you are done using it, that space is wasted, so you should have freed it earlier. But if you free it too early, well, then if you try and use it after that, that's a use after free. That's undefined behavior. Something bad will happen. And then also if you screw up and call free twice on it, that is also undefined behavior. So it's a lot harder to get right. And also, we'll briefly talk about how we would actually implement something like malloc, because if you are implementing it, there is a new concern we have to be concerned about, and that is fragmentation. We saw it come up with file systems. Basically, that is just wasted space, which we want to avoid at all costs. So it's also a unique issue for dynamic memory allocation, because we allocate memory of different sizes. They all have to be contiguous, so that's one of the rules of malloc. It returns you a contiguous block of memory. I can't do something like compact the memory, so it's not possible because every allocation decision is permanent. So as soon as I get a pointer back from malloc, malloc can't change that pointer. It has to stay the same. In Java, you get back a reference, and Java can actually move memory around for you without you noticing. As long as it fixes up all the pointers to make sure they are consistent, it's fine. So Java, because it uses references and has like a layer of indirection, it can actually move memory for you, so it could compact memory. If I had like, I don't know, some unused space between two blocks of memory, I could actually move one block to be contiguous with the other block and move them all together. With malloc, though, we can't do that because the allocation decision is permanent until you actually free it. And again, a fragment is a small contiguous block of memory that cannot handle an allocation, so I can't use it to actually fulfill the request anymore. Think of it as a whole, wasted space, whatever you want to think of it as. And for dynamic allocation, in order to have fragmentation, I need 3 requirements. So they all have to have different lifetimes. So that just means you don't alloc all at once and you don't free all at once. You have no idea what order the malloc and free can come into. If everything had the exact same lifetime, you don't have the problem of fragmentation. So with stack variables, they all live for as long as the function lives. So I just allocate them contiguously. They all live the same amount of time, so I can all free them together in a giant chunk. There won't be any holes. I can use all that space because they live for the same amount of time. Also, if I have the same sized allocation, like with virtual memory pages, every page is as good as another, I don't have to worry about fragmentation. Everything's the same size. But with malloc, you have to serve a request of any size. You can malloc 2 bytes, 2,000 bytes, whatever. You don't have any control over what the user asks for. And then third is that compaction thing. So I can't actually move any of the previous allocations and try and reduce fragmentation that way. So there's internal and external fragmentation like we talked about before. External fragmentation is when you allocate 2 different sized blocks and there's no room for allocation between the blocks. So for example, this is my allocation, or this is the memory I'm managing. Red is some allocated space already. And then I have 2 free blocks here that could be used for the allocation, but they have this one in the middle separating it out. So let's say this is size 2 and this is size 4. If an allocation comes in of size 6, well then I can't fulfill it at all because I don't have 6 contiguous blocks, even though I have 6 blocks total free, or 6 bytes total free. And then we might have some internal fragmentation. This is what we still have for file system. That occurs when you allocate a fixed size block and there's wasted space within a block. So for example, if my memory allocator only gave you pages at a time, like 4096, and I only used slightly over half of it, then all those other bytes would be considered internal fragmentation. I can't use them to do any other allocations. So we want to minimize fragmentation here, just wasted space, which we should prevent. So one idea might be reduce the number of holes between blocks of memories, and if we do have a hole, keep them as big as possible. So external fragmentation just depends on the size of the allocations. If we can fulfill the request, then we don't have any external fragmentation, we're good. So we want to keep allocating memory without wasting space. So most malloc implementations, at least the simple ones, usually use a free list. Unlike a free list of pages, they would have to keep track of how big each free block of memory is. So keeps track of free blocks of memory by chaining them together, and also would include the size, implemented with a linked list. Everyone loves linked lists. We need to handle a request of any size. So how this will work, the easiest thing to do is for an allocation, just choose a free block large enough to satisfy the request, remove it from the free list. If we have to split it out, if it's too big, we can split it into an allocated chunk and a smaller free chunk. And then for deallocation, we just add that block back to the free list. If it's beside another free block, we could coalesce them or make them a larger contiguous block, so we just join them back together so we can handle a larger request and merge them, coalesce them, whatever term you want to use. So in general, there are 3 heap allocation strategies. One is best fit, so that means we choose the smallest free block that can satisfy the request. We would need to search through all the whole list, unless there's an exact match, and in which case, can't do any better than that. So we would choose that block. There's also worst fit, which means we choose the largest block whichever has the most leftover space, that hopefully will make that space smaller and smaller and smaller. It would also have to search through that whole list again. And then we could just do the simplest strategy, which would not require, in the worst case, or in every case, searching through the whole list. And we can do first fit, so we just choose the first free block that fits the request. So let's have a little example. So if we choose the best fit strategy, and here blocks with the blank background are free, so I assume that this whole line here is all of the memory I am managing if I am malloc, and each colored block is an allocation, so I can't move it or do anything with it. So I have a red allocation here, then I have a free block of 100 bytes, then I have a bigger blue allocation here, and then a free block of 60 bytes. So now if someone requests 40 bytes, where do I put it? So if I'm doing best fit, do I put it in the 100 hole or the 60 hole? The 60, right? Best fit is whatever is the closest one. If there's an exact match, it would go there. So 60 is closer to 40 than 100 is. So I would put the allocation there, and then, well, I only need 40 of those 60 bytes, so I would split it off, and then I would have 20 left. You could put before or after, whatever makes you feel good, but now I'm done that allocation. Then I have this purple allocation. Where can I put that? In the 100, right? I can't put in the 20, it's not big enough. So I put in the 100 and I split it off. What is the remaining space after the allocation, the 100 block? 40, right? Simple math. Like I said, you don't really need a calculator for this course. So put the allocation there. Now we have 40 bytes left over. Now if we have a pink allocation for 60 bytes, we are now screwed, right? We can't do this allocation because even though we have 60 bytes remaining, we don't have 60 contiguous bytes. So if we are malloc, we would return failure or out of memory or whatever, right? So let's see what would happen if we do worst fit. So worst fit, I pick the biggest block instead of the smallest one that can fit it. So now if I replay it again, I have the green 40. Where do I put it? In the 100, right? Worst fit, the 100 is the biggest one. So I put it in the 100, split it off, there'd be 60 left, and then you can probably see where this is going, right? Purple allocation comes in, well, I put it in that 60, one of them, doesn't matter in this case, and then I have the pink block, and it fits, right? Fits exactly in the remaining space. So looks like worst fit is actually the best fit. That's a terrible joke. Don't confuse that with the other. Oh, geez. That was undeserved. So you might think the names are a bit silly, but really, I'll spoil it for you. They're both slow. So if you actually simulate this on traces from real programs, best fit actually tends to work out a bit better because it tends to leave very large holes and very small holes. Small holes might be considered external fragmentation, but the very large holes that can actually satisfy more requests. So it turns out to be all right. If you simulate worst fit, it actually says it is the worst in terms of storage utilization, so don't worry, it is not named that for no reason. But first fit is generally the quickest thing to implement because only in the worst case do I have to search the entire list. And if you simulate it, it tends to leave average size holes. So if you do have to implement it, most things will probably do something like first fit because, well, that's the easiest and fastest thing to do. So questions about that? That was fun, huh? So like I said, course is wrapping up, so we're pretty much done. So the kernel has to implement its own memory allocations. Concepts are the same for user space memory management. Kernel just gives them more contiguous virtual memory pages, so it just gives them a heap and then use the same ideas, but they'd be implemented in malloc. If you're the kernel, you would have your own version of malloc that you use internally because you don't have a standard C library. So we briefly went over static and dynamic memory allocations. For dynamic allocations, aka if we were implementing malloc, fragmentation is a big concern. For dynamic allocation, returns blocks of memory. Fragmentation between blocks is external. Fragmentation within a block is internal. And there are 3 general allocation strategies for different fixed size allocations: best fit, worst fit, and first fit. So we're pretty much done before, so I'll stay here, work on lab 6, ask me any questions you want. Like I said, I'm keeping it light because our exam is the first week, which is awful. I have finished writing the exam because I have to submit it 10 business days before. So your exam is written and submitted. So we'll have a little bit of content that will be covered on the exam in the next 2 lectures. And then our final lectures after that I will dedicate for review to make sure we are all good for the final and everyone will do greatly. Is that a word? That's not a word. But anyways, I'll stay here. Just remember,